Hello, my dear friends. Whether you're here to unwind after a long day, to quiet a racing mind, or to simply drift into a world of fascinating ideas, I'm so glad you found your way here. Tonight, we're embarking on an incredible journey into the silent, invisible heart of our modern world. We're going to unravel the story of arguably the most important invention of the last century. A story that begins in the bizarre realm of quantum ghosts and ends in the smartphone in your pocket. This is the epic tale of the transistor. It's a story of human genius, fierce rivalry, and a tiny device that changed everything. So get comfortable, relax, and let your curiosity take over. And while you're here, becoming a part of our growing community of curious minds would mean the world to me. If you're enjoying this journey, please hit that subscribe button and give this video a like. It truly helps this channel grow and reach more people just like you. I'm always so curious about where in the world this channel is helping people learn and relax, so if you feel like it, drop a comment below and tell me where you're watching from and what time it is for you right now. Are you cozying up for a late-night study session in Toronto? Is it a rainy afternoon in London? Or maybe an early morning coffee in Sydney? Let me know. Alright, without further ado, let's dim the lights and begin our story. Imagine a world silenced, not a quiet world, a truly silenced one. No radio voices weaving stories through the air, no television screens painting moving pictures in our living rooms, no smartphones, those sleek slabs of glass and metal that connect us to the entirety of human knowledge and to each other, instantly. No internet humming with invisible data, no satellites beaming signals across continents, no guided missiles, no calculators, no digital watches, no modern cars, no pacemakers ticking in time with a human heart. Imagine a world where the computer, that machine that now defines our age, is a room-sized beast, filled with thousands of fragile, glowing glass tubes, gulping down enough electricity to power a small street, and failing, constantly failing, as those tubes burnt out like so many tiny spent suns. This was our world, not so long ago. A world before the tiny, simple, and yet almost magical key that unlocked our modern era. A world before the transistor. Our story doesn't start with a flash of genius in a Silicon Valley garage, but in the deep, puzzling, and wonderfully strange realm of theoretical physics. To understand the transistor, we must first take a little detour into the heart of the atom itself, into a world that defies our everyday common sense. You see, by the early 20th century, scientists had gotten very good at explaining the big things: planets, cannonballs, steam engines, with the physics of Isaac Newton. It was a world of certainty, of predictable paths, of balls rolling down hills. But when they peered into the atom, this comfortable clockwork universe fell apart. Here things were fuzzy, probabilistic, and downright weird. This was the birth of quantum mechanics, and it would rewrite the rules of reality. Let's try to picture this. Imagine an electron, one of the tiny particles orbiting the nucleus of an atom. In our old Newtonian view, we might think of it as a miniature planet, whizzing around a miniature sun in a neat, predictable orbit. Quantum mechanics tells us this picture is completely wrong. An electron doesn't live on a tidy little lane. It's more like a hyperactive ghost that exists as a cloud of probability, a wave of potential. It doesn't have a single, precise location and speed at the same time, a concept known as the Heisenberg uncertainty principle. It exists in a blur of could be here and could be there. This electron cloud is denser in some places than others, meaning you're more likely to find the electron there, but you can never be certain until you look. It's like a spinning coin. It's neither definitively heads nor tails until you slam your hand down on it. The act of observation itself forces the electron to make up its mind and settle into a specific state. This is the bizarre, counterintuitive foundation upon which our modern world is built. Now, these electrons exist in specific energy levels, or shells, around the atom. Think of them as a set of fixed concentric stairs. An electron can be on the first step, or the second, or the third, but it can never stand in the space between the steps. It can, however, jump. If it absorbs a tiny packet of energy, called a quantum, it can make a leap up to a higher step. Conversely, when it falls down to a lower step, it spits out that same packet of energy, often in the form of a particle of light, a photon. This is the quantum leap. It's not a big, vague change. It's a precise, instantaneous jump from one discrete state to another. So, what does this have to do with a device that lets you watch cat videos on your phone? Everything. Because the behavior of electrons in solids, particularly in certain materials called semiconductors, is the very soul of the transistor. To understand that, we need to talk about how atoms come together to form solids. When a vast number of atoms, say silicon atoms, arrange themselves into a regular repeating crystal lattice, something fascinating happens to those individual electron energy levels. They don't just stay as single steps, they smear out, merging and splitting into vast collections of so many closely spaced levels that they become continuous bands. Imagine a single guitar string playing one note. That's an electron in a single atom. Now imagine 1,000 guitar strings, all tuned microscopically differently, playing at once. The sound becomes a continuous, rich chord. That chord is the energy band in a solid. In any material, you essentially have two important bands, the valence band and the conduction band. The valence band is like a crowded dance floor where all the electrons are, happily holding hands with their neighboring atoms, forming the chemical bonds that keep the solid together. They're involved, but they're not free to move. The conduction band, high above it, is like an empty, wide-open hallway. If an electron can get enough energy to jump from the crowded dance floor up into that empty hallway, it becomes a free electron. It can zip through the material, and the flow of these free electrons is what we call electricity. The key is the gap between these two bands, the band gap. It's the energy jump an electron needs to make to go from being bound to being free. This band gap determines whether a material is an insulator, a conductor, or a semiconductor. In an insulator like rubber or glass, the band gap is huge. It's like the dance floor is 10 stories below the empty hallway. The electrons simply can't make that jump. They're stuck on the dance floor and no current can flow. In a conductor like copper or silver, there is no gap at all. The dance floor and the hallway are on the same level, and some electrons are already in the hallway, milling about freely. Apply even a tiny voltage, and they'll all start running in the same direction. A current flows easily. Then we have the Goldilocks material, the semiconductor. Here, the band gap is small, not impossible like in an insulator, and not non-existent like in a conductor. It's just right. At absolute zero temperature, a semiconductor acts like a perfect insulator. All the electrons are on the dance floor. But at room temperature, a few of the more energetic electrons get a little thermal kick, enough to make the jump across the small gap into the conduction band. They leave behind a hole on the dance floor. Now, this hole isn't just an empty space. In the quantum world, the absence of a negative charge behaves exactly like a positive charge. It's like a bubble in a liquid. The bubble isn't a real thing, it's a lack of liquid, but it moves and behaves with a personality of its own. So when a nearby electron jumps in to fill this hole, it effectively makes the hole move to a new location. This movement of positive holes is just as valid a form of electrical current as the movement of negative electrons. In a pure or intrinsic semiconductor like silicon, for every free electron that jumps to the conduction band, a positively charged hole is created in the valence band. They are generated in pairs. This was interesting, but not yet revolutionary. The magic, the true spark of genius, came when we learned to control this process by deliberately introducing impurities into the ultra-pure semiconductor crystal. This process is called doping, and it's what turns a passive material into an active, intelligent one. Let's stick with our silicon example. A silicon atom has 4 electrons in its outer shell that it uses to bond with its 4 neighbors. Now imagine we carefully introduce a tiny, precise amount of an impurity atom that has 5 electrons in its outer shell, like phosphorus. This phosphorus atom fits into the crystal lattice where a silicon atom would be. It uses 4 of its electrons to bond with its 4 silicon neighbors, but the 5th electron is left over. It's not needed for bonding. It's very loosely bound to its parent phosphorus atom, so loosely that at room temperature it's already kicked up into the conduction band, ready to roam freely as a charge carrier. Crucially, when it leaves, it doesn't create a hole in the valence band. The phosphorus atom, now called a donor impurity, becomes a fixed positive ion, but the electron it donated is free to move. This type of doped semiconductor is called N-type, where N stands for negative, because the majority charge carriers are free, negative electrons. Now consider the opposite. What if we dope the silicon with an atom that has only 3 electrons in its outer shell, like boron? This boron atom fits into the lattice and tries to bond with its 4 neighbors, but it only has 3 electrons. It's one short. This missing bond acts as a hole, ready to accept an electron. At room temperature, an electron from a neighboring silicon atom will easily jump over to fill this hole. This movement leaves a hole behind at the silicon atom, and effectively, the hole has moved. The boron atom, now called an acceptor impurity, becomes a fixed negative ion, but the hole it created is free to move through the crystal as a positive charge carrier. This is called p-type semiconductor, where P stands for positive, because the majority charge carriers are positive holes. So now we have our 2 magical ingredients, p-type silicon, which is teeming with movable positive holes, and N-type silicon, which is teeming with movable negative electrons. By themselves, they are just slightly better conductors. But when you join them together, you create something extraordinary, a p-n junction. This is not like pushing 2 different blocks of wood together. At the atomic level, where the p-type and N-type materials meet, a fascinating dance occurs. Right at the junction, the free electrons from the N side, seeing all the empty holes on the P side, diffuse across the boundary to fill them. Similarly, the holes from the P side diffuse into the N side. But this movement of charges has a dramatic consequence. As electrons leave the N side, they leave behind the fixed positive donor ions, the phosphorus atoms that lost their electron. This creates a thin layer on the N side of the junction that is positively charged. On the P side, as holes leave, which is equivalent to electrons arriving, they leave behind the fixed negative acceptor ions, the boron atoms that gained an electron. This creates a thin layer on the P side that is negatively charged. So, across this junction, a natural electric field is created from the positive N side to the negative P side. This region is called the depletion region because it has been depleted of its free charge carriers. This built-in electric field acts as a barrier, a hill. It now prevents any further diffusion. An electron on the N side would have to climb this electric hill to get to the P side. A hole on the P side would have to climb the same hill, from its perspective, to get to the N side. At equilibrium with no external voltage, the traffic stops. The junction is at a standstill. Now let's apply an external voltage. This is where we get control. If we connect the positive terminal of a battery to the P side and the negative terminal to the N side, this is called forward bias. What we're doing is using the battery to oppose the built-in electric field. It's like using a powerful pump to push against the natural hill. The positive voltage on the P side repels the holes towards the junction. The negative voltage on the N side repels the electrons towards the junction. This injection of charge carriers shrinks the depletion region and lowers the energy hill. If the battery voltage is high enough to completely overcome the built-in barrier, a massive current can flow. Electrons surge from the N side to the P side, and holes surge from the P side to the N side. The junction becomes a very good conductor. But reverse it. Connect the positive terminal to the N side and the negative to the P side. This is reverse bias. Now, the external battery voltage reinforces the built-in field. It makes the hill even steeper and wider. The positive voltage on the N side pulls the electrons away from the junction. The negative voltage on the P side pulls the holes away from the junction. The depletion region widens into a vast charge-free desert. Almost no current can flow. A tiny trickle, called reverse saturation current, might exist due to thermally generated minority carriers, but it's negligible. The p-n junction now acts as a nearly perfect insulator, a one-way street for current. It's a diode, an electrical check valve. The diode was a crucial first step, a device born directly from quantum mechanical principles applied to doped semiconductors. It could rectify alternating current, AC, into direct current, DC, a fundamental task in electronics. But it was an on-off device, a switch with no middle ground. The next monumental leap was to create a device that could not only switch but also amplify. A device where a small signal could control a much larger one. This was the Holy Grail, and it was the problem a brilliant team at Bell Laboratories was tasked with solving in the post-war years. After years of painstaking work, of theoretical breakthroughs and ingenious experimentation, the moment of creation arrived on December 16, 1947. Brattain and Bardeen built a bizarre-looking contraption. They took a slab of germanium, an N-type semiconductor. They placed two gold foil contacts very, very close together on the top surface, and just below them they had a third contact for the base. This device, which looked more like a crude science project than a world-changing invention, was the first point-contact transistor. When they applied a small current to one of the point contacts, the emitter, it modulated the current flowing through the other point contact, the collector, with the power supplied by the base. Crucially, the output power was greater than the input power. They had achieved amplification. The small signal was controlling a large one. The solid-state revolution had begun. Shockley, who was leading the group, was reportedly furious that he wasn't directly involved in this breakthrough. You see, while William Shockley was the official leader of the team, the breakthrough that had finally cracked the solid-state amplifier problem belonged squarely to John Bardeen, the quiet theorist, and Walter Brattain, the gifted experimenter. Shockley, a man possessed of a towering intellect and an equally towering ego, was reportedly furious. There's a famous story that he confronted both men shortly after their successful demonstration and told them, in no uncertain terms, that sometimes the people who do the work don't get the credit for it. He felt that his initial direction and his field effect concept were the true seeds of the invention, and he was determined to secure his place as the sole originator. He embarked on a campaign with the company's lawyers to patent the transistor under his name alone, a move that left Brattain shouting that there's more than enough glory in this for everybody, and Bardeen fuming in silent stoic resentment. The rift was not just personal. It was a fundamental crack in what had been, for a brief glorious period, a perfect symbiotic relationship. So, what did Shockley do? He didn't just sulk. Instead, he channeled that ferocious competitive energy into a spectacular burst of what can only be called competitive genius. He essentially hid himself away, holed up in a Chicago hotel room, and for the next few weeks, he single-mindedly pursued a single goal: to conceive of a transistor that was not only better than the point contact device, but was so fundamentally different and superior that it would eclipse the work of his colleagues and secure his legacy. And in a remarkably short period, he did just that. He conceived the theory for the bipolar junction transistor, or BJT, a device that would indeed become the classic, robust workhorse of the electronics industry for decades to come. This was Shockley, the visionary at his best, looking beyond the fragile, finicky contraption of gold foil and a plastic wedge, and imagining a device that was inherently more stable, more reliable, and far more suitable for mass production. Now, to understand why Shockley's BJT was such a leap forward, we first need to appreciate the quirks and frailties of that first point contact transistor. The device that Bardeen and Brattain built was, to put it bluntly, a bit of a delicate flower. It relied on two gold metal points making precise, almost impossibly close contact with the surface of a germanium crystal. These point contacts were notoriously fragile and difficult to manufacture consistently. The device was sensitive to changes in temperature, and its characteristics could vary wildly from one unit to the next. It worked. It proved the concept magnificently, but it wasn't something you could easily imagine being stamped out by the millions on a factory floor. It was, in essence, a brilliant proof of concept, a scientific triumph that now needed an engineering revolution to become truly practical. This was the problem Shockley set out to solve with his junction transistor. His brilliant insight was to move away from the tricky physics of surfaces and point contacts altogether. Instead of poking the surface of a semiconductor, why not build the entire function directly into the bulk of the material itself? His solution was as elegant as it was revolutionary. He proposed a layered sandwich of semiconductor materials. Imagine, if you will, a club sandwich. But instead of bread, turkey, and bacon, we have layers of semiconductor material with different electrical characteristics. In the most common and classic configuration, the NPN transistor, you would have a thin, lightly doped slice of p-type semiconductor acting as the filling, and on either side of it, two slabs of n-type semiconductor acting as the bread. No more delicate gold points precariously touching the surface. This was a solid, monolithic structure where the magic happened internally, within the crystal itself. Let's give these three layers their names that have become legendary in electronics. On one end of the sandwich, we have the emitter. Its job is exactly what it sounds like, to emit or inject charge carriers into the sandwich. This layer is typically heavily doped, meaning it's absolutely teeming with mobile electrons, ready to be sent on a journey. On the opposite end, we have the collector. Its job is to collect or gather up these charge carriers after their journey. This layer is usually larger and moderately doped, designed to efficiently sweep up the incoming electrons. And in the middle, the thin, lightly doped p-type layer, we have the base. This is the control center, the gatekeeper, the heart of the entire amplification process. Its name comes from the fact that it forms the base electrode of this new structure, but its function is anything but basic. This three-layer two-junction structure was a complete departure from the single piece of germanium with point contacts, and it was this architectural genius that defined Shockley's contribution. Now, within this semiconductor sandwich, we don't have just a homogeneous block of material. Where these different layers meet, something extraordinary happens. We get what are known as PN junctions. Think of a PN junction as a one-way street for electric current, a kind of electrical diode. Between the emitter and the base, there is one PN junction. Between the collector and the base, there is another. So in an NPN transistor, you have back-to-back PN junctions, creating a kind of natural barrier within the device. In its normal state, with no external voltages applied, these junctions prevent any significant current from flowing from the emitter to the collector. It's like having two one-way streets facing opposite directions. You just can't drive through. The key to making the transistor work is to apply strategic voltages to these three layers to open up a pathway, and this is where the quantum ballet of electrons and holes takes center stage. To get our NPN sandwich to amplify, we need to bias the junctions properly. This is a fancy way of saying we need to apply specific voltages to each layer to put them in the right operational mood. We forward bias the emitter-based junction. Remember what forward bias does from our earlier chat? It lowers the energy hill, making it easy for charge carriers to cross. So we make the base slightly positive relative to the emitter. This positive voltage on the p-type base repels the positive holes away from the junction, but more importantly, it attracts the negative, electron-rich n-type emitter. It effectively lowers the barrier, and electrons come flooding out of the heavily doped emitter, across the junction, and into the very thin p-type base. It's like opening a floodgate from the emitter into the base. Now, here comes the most beautiful part of the whole dance. These electrons, now injected into the base, find themselves in a strange land. The base is p-type, which means its majority carriers are holes, the very opposites of electrons. An electron and a hole are desperate to recombine. It's their natural instinct. If they meet, they annihilate each other in a tiny burst of energy, and that electron is gone from the current. But Shockley's design is so clever. The base is made incredibly thin, so thin that most of these injected electrons surging into the base don't have time to find a hole to recombine with. They are like a crowd of people poured into a very narrow, short corridor. They are moving so fast and the corridor is so short that they just spill out the other side before they can find a door to exit. And what's waiting for them on the other side of this thin base? The collector-based junction. And this junction, cleverly, is reverse biased. We make the collector highly positive relative to the base. Now, a reverse bias junction is normally a huge blocking barrier. It's a tall energy hill that the majority carriers in the base, which are holes, cannot climb. But for our incoming electrons, which are minority carriers in the p-type base, that reverse bias junction doesn't look like a hill at all. It looks like a steep, attractive cliff. The strong electric field in the depletion region of the collector-base junction sees this cloud of electrons arriving and violently grabs them, sucking them across the junction and into the collector. It's like a powerful vacuum cleaner positioned right at the exit of that narrow corridor, pulling the electrons through. So, let's trace the entire journey. A small current flowing into the base terminal, this is our small, weak input signal, is used to forward bias the emitter-base junction. This small base current controls the flood of electrons from the emitter into the base. The vast majority of these electrons then get swept up by the electric field and collected by the collector, creating a much larger current in the collector circuit. Crucially, a tiny variation in the small base current results in a large proportional variation in the large collector current. The small signal is controlling the large one. Amplification is achieved. This is the transistor effect in its most elegant form, and it's why this device is called a bipolar junction transistor, because the current flow involves both types of charge carriers, negative electrons and positive holes, both playing their part in the grand scheme. The superiority of this junction transistor over the point contact type was immediately apparent to everyone at Bell Labs. It was more robust, less noisy, and its properties were more predictable and easier to control. It wasn't without its own manufacturing challenges initially. It would take a few more years for the technology to catch up and produce reliable junction transistors. But the path forward was now clear. Shockley had indeed succeeded in his goal of creating a theoretically superior device. However, this triumph came at a great personal cost to the team. The atmosphere became so toxic, with Shockley actively blocking Bardeen and Brattain from working on the new junction transistor, that the collaboration shattered. Bardeen, describing the situation as intolerable, left Bell Labs in 1951 for the University of Illinois, where he would later win his second Nobel Prize for the theory of superconductivity. Brattain, too, asked to be transferred to another research group, wanting nothing more to do with Shockley. The three men who had created a revolution were ultimately driven apart by the very forces of ambition and ego that had, in part, fueled their success. They would meet again, most famously in Stockholm in 1956, to receive the Nobel Prize in Physics for their joint invention, but by then their paths had irrevocably diverged. And so, from the friction and fractured partnership of three brilliant minds, two foundational devices of the electronic age were born: the point contact transistor, a testament to collaborative experimentation and theoretical insight, and the bipolar junction transistor, a monument to individual genius and competitive drive. The BJT, born from Shockley's furious isolation, would indeed become the cornerstone of electronics for decades, paving the way for the integrated circuit and the microprocessor. It was a classic case of a messy, very human story producing an object of pure, transformative brilliance. The simple, robust sandwich of semiconductor materials had arrived, and it was ready to change the world. You see, when the transistor was first announced to the world in 1948, the excitement was, well, a bit confined to the hallways of Bell Labs and a few other physics labs. To everyone else, it was a nifty scientific novelty, but not much more. Imagine showing a single, perfect, hand-cut diamond to a jeweler in the 1800s and telling him that one day these would be so common and perfectly made that they'd be used in every watch and piece of electronic equipment in the world. He'd have thought you were mad. That was the transistor. The first point contact transistors were famously described as looking like a crude science project, and in a way, they were. They were put together by hand with bits of gold foil and a plastic wedge, and they were fragile. Bump one too hard, and those precisely spaced point contacts would be knocked out of alignment, and the magic would stop. Manufacturing them consistently was a nightmare. No two seemed to behave exactly the same way. They were like exotic, temperamental orchids, beautiful in the lab but not ready for the rough and tumble of your average factory floor or, heaven forbid, a commercial product. But oh, the potential. Anyone with the vision could see it. Here was a device that was solid, with no fragile glass envelope to break and no delicate heated filament inside that would inevitably burn out, like in a vacuum tube. It used a minuscule amount of power, and it didn't need a warm-up time. You could flip a switch and it was on instantly. and perhaps most importantly, it produced far, far less heat. This was a huge deal. The early room-sized computers like the ENIAC were built with thousands of vacuum tubes, which were like little light bulbs. They consumed enough electricity to power a small neighborhood, and the heat they generated was so immense that the rooms they were in required complex and powerful cooling systems just to keep them from melting themselves into a puddle of solder and glass. The transistor promised to change all of that. It promised to make electronics cool, quiet, small, and reliable. So, who was the first to truly see this value? Well, as with many technological leaps, it was the military. They saw a device that could make their communications equipment more rugged and portable, that could extend the battery life of field radios, and that could enable the development of more complex and powerful guidance systems for missiles and aircraft. They provided the initial funding and the demanding real-world problems that helped push transistor technology from the lab bench into initial production. But hot on their heels were the burgeoning computer and consumer electronics industries. The people dreaming of the future of computing saw a path out of the tube age, a path that could lead to computers that weren't the size of a living room. And the consumer electronics pioneers saw a chance to untether electronics from the wall socket. The first major commercial application wasn't a computer, though. It was something much more personal and portable. The hearing aid, followed rapidly by the transistor radio. For the first time, you could have a powerful electronic amplifier that was small enough to fit in your ear or your pocket, and battery-powered enough to last for more than a few minutes. The Regency TR-1, released in 1954, and the Sony TR-63, which hit the market in 1957, didn't just play music. They announced to the world that the era of personal portable electronics had officially begun. The solid-state revolution was no longer a theory. It was something you could hold in your hand. Now, as wonderful as this was, there was a new problem on the horizon. As circuits became more complex, requiring dozens, then hundreds of transistors, along with all the resistors, capacitors, and the tangled web of wires needed to connect them, a new kind of bottleneck emerged. It was nicknamed the tyranny of numbers. Imagine a city planner trying to build a metropolis for millions of people, but instead of designing roads and intersections, he had to individually place and connect every single brick in every single building by hand. The complexity was becoming unmanageable. The circuit boards were getting crowded, the soldering points were becoming microscopic, and the sheer number of connections meant that the chances of a tiny, almost invisible soldering fault causing a catastrophic failure were skyrocketing. The individual transistors were reliable, but the mind-boggling complexity of wiring them all together was threatening to halt progress in its tracks. This is where the next great leap of imagination comes in. An idea so beautifully simple in concept, yet so fiendishly difficult in execution that it would require its own revolution in manufacturing to achieve. The question was posed by two brilliant men independently and almost simultaneously, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor. Their question was why? Why must we painstakingly manufacture all these components separately, the transistors, the resistors, the capacitors, and then have people or machines solder a rat's nest of tiny wires to connect them all together on a circuit board? Why not, they thought, do the opposite? Why not manufacture an entire electronic circuit, all of its components and the connections between them out of a single solid piece of semiconductor material? Instead of an assembly of discrete parts, you would print or sculpt the entire circuit as one complete, unified, and indivisible unit. This was the breathtakingly simple concept that led to the birth of the chip, or as it was formerly known, the integrated circuit, the IC. The process to make these chips is, without exaggeration, one of the most complex and precise manufacturing feats humanity has ever achieved. It's a form of atomic scale sculpture, and it starts with a base material of almost impossible purity. That base is a wafer, a thin, pristine disk of extremely pure silicon grown as a single perfect crystal. This isn't like the crystalline sugar in your kitchen. This is a crystal where the atomic structure is nearly flawless, a repeating lattice of silicon atoms that provides the perfect orderly canvas upon which the microscopic circuits will be drawn. This silicon wafer starts out as a blank slate, a perfect, shiny, and featureless disk. Onto this blank canvas, a long and intricate series of processes begins, a dizzying dance of chemistry, physics, and optical precision. The first key step is often oxidation, where the wafer is heated in a precise environment to grow a thin, uniform layer of silicon dioxide right on its surface. This layer is an excellent insulator. It's like the chip's own personal sheet of glass, and it will be used to protect areas of the silicon and to create the critical gates in transistors. Then comes the true heart of the entire operation, the step that makes modern electronics possible: photolithography. The name sounds complicated, but the concept is like using a microscopic stencil, or perhaps a form of atomic-scale photography. Here's how it works. First, the wafer is coated with a photosensitive chemical called photoresist, which is spun at high speed to create a layer so thin and uniform it's almost unimaginable. Then, using a multi-million-dollar machine called a stepper, an intricate pattern of ultraviolet light is projected onto the wafer's surface. This light isn't shown randomly. It's passed through a mask, which is like a high-precision photographic negative of the circuit, but with details so small they are measured in nanometers. Where the light hits the photoresist, it hardens, undergoing a chemical change. The areas shielded by the patterns on the mask remain soft. Next, the wafer is developed, much like a photograph in a darkroom. A chemical solution washes away the unexposed, soft areas of photoresist, leaving behind a perfect, hardened stencil of the circuit pattern on the wafer. Now, with this stencil in place, the real magic of transformation happens. The wafer is like a piece of metal with a protective coating that has specific, precise cutouts. We can now do one of several things to the exposed silicon. We can dope it by bathing it in a gas of impurity atoms, like boron or phosphorus, that diffuse into the silicon in a process called, fittingly, diffusion. Or we can blast the atoms into the silicon with high energy in a process called ion implantation. This carefully controlled contamination is what creates the N-type and P-type regions that form the transistors themselves. Alternatively, we can use a different chemical to etch away the exposed silicon dioxide insulator that we grew earlier, carving out tiny trenches. Or we can deposit a thin layer of metal, like aluminum or copper, over the entire surface, which will coat the stencil and settle into the etched trenches and contact points, forming the microscopic wires that will eventually connect all the transistors together. After this, the remaining hardened photoresist is stripped away, leaving behind the newly created structures. And here's the truly mind-bending part: this entire sequence, coating with photoresist, exposing it to light through a mask, developing it, and then either doping, etching, or depositing metal, is not a one-time thing. It is repeated dozens of times, sometimes over 30 times, layer upon layer upon layer. Each cycle uses a different mask with a different pattern, building up the complex three-dimensional structure of the circuit with a precision that defies belief. It's like building a vast, multi-level, microscopic city with streets, overpasses, and buildings all from the ground up on a canvas the size of your fingernail. And on that single wafer, dozens, then hundreds, and now thousands of individual chips are created simultaneously, like cookies on a baking sheet, before being sliced apart into individual units, each one a complete electronic circuit containing first a few, then millions, and now billions of transistors. This relentless exponential miniaturization, this drive to make transistors smaller and pack them closer together, has a name. We call it Moore's Law. It's not a law of physics, but an observation and a prediction made by Gordon Moore, one of the co-founders of Intel, back in 1965. He observed that the number of transistors that could be economically placed on an integrated circuit was doubling approximately every 2 years. This observation became a self-fulfilling prophecy, a roadmap for the entire semiconductor industry. For decades, it held true, acting as the primary engine of the digital revolution. As transistors shrank, they became faster because electrical signals had less distance to travel. They became cheaper to produce per transistor, and they became vastly more power efficient. This is why the smartphone in your pocket is millions of times more powerful than the computers that guided the Apollo missions to the moon. It's all thanks to the unimaginable density of tiny, efficient switches we can now manufacture. But as with any great journey, we are now reaching new and uncharted territories. As we have pushed deeper into the nanoscale, the cozy, predictable world of classical physics that we live in every day has begun to break down. We are now building transistors where the critical dimensions are just a few dozen atoms across. At this scale, the weird and wonderful rules of the quantum world, the very rules that gave us the transistor in the first place, have begun to reassert themselves in new and challenging ways. One of the biggest challenges is a phenomenon called quantum tunneling. In our everyday world, a ball can't roll through a solid hill. It has to go over it. But in the quantum world, an electron, which behaves as both a particle and a wave, has a finite probability of just tunneling straight through an energy barrier that it classically shouldn't be able to cross. When the insulating layers in a transistor are only a few atoms thick, electrons can play this trick, tunneling from one part of the transistor to another when they're not supposed to, causing leakage currents that waste power and generate heat. It's as if a light switch started letting little sparks of light through even when it was in the off position. This quantum tunneling represents a fundamental physical limit to how small we can make conventional transistors, forcing the world's most brilliant engineers to invent new, three-dimensional transistor structures and to explore entirely new materials, and, perhaps one day, a whole new paradigm of computing based on quantum mechanics itself, bringing our story full circle in the most beautiful and mysterious way. So, engineers didn't fight quantum mechanics, they embraced it. They started designing transistors that explicitly relied on quantum effects. The most successful of these is the metal oxide semiconductor field effect transistor, or MOSFET, which is the workhorse of modern digital logic, the transistor in your computer's CPU and your phone's processor. It is a perfect moment in our story where human ingenuity stopped trying to force the quantum world to behave like our comfortable, large-scale one, and instead learned to dance to its strange, subatomic rhythm. The MOSFET is the ultimate expression of that dance, a device that is so profoundly quantum mechanical from its very conception that it almost feels like magic. So, let's pull back the curtain on that magic. The story of the MOSFET begins not with a eureka moment in a lab, but with a problem that had stymied the very inventors of the transistor. Decades before Bardeen, Brattain, and Shockley created their point contact device, the principle of the field effect transistor had already been patented, but when they tried to build it, it simply wouldn't work. The semiconductor surface was a messy, unpredictable place, riddled with what are called surface states, traps that would capture and immobilize electrons, preventing the electric field from having any controlling effect. It was like trying to steer a car by remote control, only to find that the signals were being absorbed by a thick, impenetrable fog. This failure led them to the bipolar junction transistor, but the dream of a simple voltage-controlled switch remained. The key that cleared the fog was a beautiful accident. In 1955, at Bell Labs, scientists Carl Frosch and Lincoln Derrick were working with silicon wafers when they accidentally grew a layer of silicon dioxide on them. They noticed something remarkable. This glassy layer didn't just protect the silicon, it passivated it. It smoothed out the chaotic energy landscape of the surface, neutralizing those electron-trapping states and creating a pristine, orderly interface between the silicon and the insulator. This discovery of surface passivation was the foundational breakthrough. It was the equivalent of discovering a perfectly smooth, frictionless surface upon which you could finally build the machine you had always dreamed of. This breakthrough circulated through the semiconductor world and was seized upon by other brilliant minds, most notably Jean Hoerni, who incorporated it into his planar process, which in turn allowed Robert Noyce to conceive of the integrated circuit. Then, in 1959, building directly on this passivation technology, two researchers at Bell Labs, Mohammed Attallah and Dawan Kang, finally succeeded. They fabricated the first working metal oxide semiconductor field effect transistor. Their first device was slow, about 100 times slower than the bipolar transistors of the day, and many saw it as a scientific curiosity, an inferior cousin. But Attallah and Kang saw its potential. They realized its supreme advantage was not raw speed, but its breathtaking ease of fabrication and its perfect suitability for being integrated into complex circuits by the thousands, then millions, then billions. They had, perhaps without even fully realizing it at the time, planted the acorn that would grow into the oak tree of our digital world. Now let's take that marvel of quantum engineering apart, piece by piece, and see how it works its sorcery. The name itself is a perfect blueprint: metal oxide semiconductor field effect transistor. In a modern chip, the metal part is often a bit of a historical relic. While the first gates were indeed made of metal, for a long time they've been made from polysilicon, a highly conductive form of silicon, though in the most advanced transistors, metals have made a comeback to solve performance issues. This gate is the control electrode, the conductor of our subatomic orchestra. It's separated from the main semiconductor body by the oxide, a layer of silicon dioxide so incredibly thin it's just a few atoms thick. This layer is an almost perfect insulator, a barrier that, under normal circumstances, no electron could cross. It's the glass in our microscopic capacitor. Finally, we have the semiconductor, typically a p-type silicon substrate, a sea of positive holes. Embedded within this substrate are two islands of heavily doped n-type silicon, teeming with mobile, negative electrons. These are the source and the drain. The source is where the electrons begin their journey, and the drain is where they are pulled towards. The region in the p-type substrate between them is the channel, the stretch of road that is, in its natural state, completely closed off. Here is where the quantum ballet begins. In its off state, with no voltage on the gate, the channel between the source and drain is like a wide, impassable river of positive charges separating two electron-rich banks. The p-n junctions between the n-type source drain and the p-type body are reverse biased. They are natural barriers and no current can flow. The transistor is a silent, dark switch in the off position. Now we take the first step. We apply a positive voltage to the gate electrode. Since the oxide layer is an insulator, no electrical current can flow into the gate from the circuit. This is a crucial point. The MOSFET is a voltage-controlled device, requiring almost no input current to do its job, which is why it's so incredibly power efficient. But what that positive voltage does create is a powerful electric field, which shoots straight down through the ultra-thin oxide layer and penetrates the surface of the p-type silicon below. This electric field is an invisible force that starts to rearrange the quantum furniture in the semiconductor. The positive charge on the gate acts like a magnet for negative charges and a repeller of positive ones. So the first thing it does is repel the positive holes in the p-type substrate, pushing them away from the surface. This creates what's called a depletion region, a zone near the surface that has been stripped of its mobile charge carriers, leaving behind only the fixed, negatively charged acceptor atoms. It's like clearing a crowd of people out of a town square, but the electric field isn't done. Having pushed the holes away, it now starts to attract the only negative charges available, the minority carriers in the p-type silicon. These are the electrons. They are drawn from the source and drain regions, and even from the bulk of the substrate towards the interface between the silicon and the oxide, right under the gate. As we increase the positive voltage on the gate, the electric field intensifies. It bends the energy bands of the silicon so dramatically that something magical happens. The surface of the p-type silicon, which was once a sea of positive holes, is now flooded with a dense mobile population of electrons. This is the inversion layer. The material at the surface has been fundamentally transformed from p-type into n-type. It's as if you used a mere whisper of electricity to convince a layer of wood to suddenly behave like metal. This inversion layer is a conductive bridge, a perfectly formed n-type channel that now connects the n-type source to the n-type drain. The once impassable river has been filled in and a highway for electrons has appeared. If a voltage is now applied between the source and drain, a massive current can flow. The transistor is decisively on. This creation of the inversion layer is where we move from classical electrostatics into the pure weird world of quantum mechanics. The electrons in this channel aren't just flowing freely in 3 dimensions. They are trapped. They are confined to an incredibly narrow potential well, a tiny slot only a few nanometers wide, created by the electric field from the gate on one side and the fundamental energy barrier of the silicon dioxide insulator on the other. Because they are squeezed into such a fantastically small space, their behavior changes fundamentally. In the direction perpendicular to the channel, their energy becomes quantized. This means they can no longer have just any energy level. They can only occupy specific discrete energy levels, like an electron trapped on specific rungs of a ladder. This phenomenon is called quantum confinement. We are no longer dealing with a three-dimensional gas of electrons buzzing around in all directions. We have created a two-dimensional electron gas, a sheet of charge where the electrons are free to move in only two dimensions, along the length and width of the channel, but not in its minuscule height. The properties of this 2D electron gas are not described by the comfortable, predictable laws of classical physics. They are governed by the probabilistic wave-like rules of quantum physics. The entire operation of the most common transistor in history, the workhorse of every microprocessor, depends on this quintessentially quantum mechanical effect. We didn't just learn to live with quantum mechanics, we built our entire modern world by harnessing it. And the journey of miniaturization, this relentless drive described by Moore's law, has only taken us deeper into the quantum realm. As we pushed the dimensions of the MOSFET channel down to a few dozen atoms, we started building devices where quantum effects don't just contribute, they dominate in all three dimensions. These are the quantum dot transistors, the next step in our quantum odyssey. In these devices, the channel is no longer a long, thin road. It is a tiny island, or dot, of semiconductor, so small that it can trap only a handful of electrons, or in the most extreme cases, a single electron. Here, another quantum phenomenon takes center stage, the Coulomb blockade. Think of the quantum dot as a tiny charged room. Because it's so small, adding a single electron to it requires a significant amount of energy to overcome the electrostatic repulsion of the electrons already in there. It's like trying to push a new person into a phone booth that's already crammed full. The people inside will push back fiercely. This energy cost creates a blockade. In a quantum dot transistor, unless the voltage you apply provides exactly the right amount of energy to pay this toll, an electron cannot tunnel onto the dot. This allows for exquisitely sensitive control of the current. You can literally control the flow of electricity one electron at a time, turning the current on and off with the precision of a master watchmaker. This isn't just a laboratory curiosity. Quantum dots are candidates for the future of ultra-low power electronics, where the precise control of single electrons could drastically reduce the energy wasted in computation. Even more profoundly, a single electron trapped in a quantum dot, with its spin state representing a 0 or a 1, is a leading candidate for a qubit, the fundamental building block of a quantum computer. So, the MOSFET, born from our understanding of quantum mechanics, is now paving the way for its own eventual successor, taking us from the age of silicon to the dawn of the quantum age, all by embracing the strange and wonderful rules that govern the very small. And this brings us to the ultimate frontier, using the transistor not just as a switch, but as a host for quantum bits, or qubits. So what exactly is this qubit? Let's start with what we know. A classical bit, the kind that has been the lifeblood of computing since its inception, is a straightforward fellow. It's like a standard light switch on your wall. It can only be in one of two distinct states, on or off, 1 or 0. There is no in-between. A transistor in a classical computer operates on this exact principle. When it's off, it's a 0. When it's on, it's a 1. Every photo, every song, every word you've ever seen on a digital screen is, at its heart, just an impossibly long sequence of these zeros and ones, orchestrated by billions of tiny transistor switches. A qubit, or quantum bit, is the quantum equivalent of this classical bit, but to say it's just a quantum version would be a dramatic understatement. It's like comparing a solo acoustic guitar to a full symphony orchestra. A classical bit is that single, clear note. A qubit is the entire orchestra, capable of playing many notes all at the same time. How is this possible? It all comes down to two of the most mind-bending and powerful concepts in quantum mechanics: superposition and entanglement. First, let's tackle superposition. Imagine that light switch on your wall. Now, imagine that instead of being definitively up or down, it could exist in a strange, fuzzy state of being both on and off at the same time. It's not that it's stuck in the middle. It's that it genuinely occupies both states simultaneously, with a certain probability of being found in one or the other when you finally look at it. This is the essence of superposition. For a qubit, this means it isn't just a 0 or a 1. It is a blend of both, a combination described by what are called probability amplitudes. You can think of it as a wave, where the crest of the wave might represent a 1 and the trough a 0, and the qubit is the entire fluid wave itself existing across the whole spectrum. A common analogy is a spinning coin. A classical bit is a coin that has landed definitively as either heads or tails. A qubit in superposition is that coin while it's still spinning on its edge. It is not heads and it is not tails. It is in a state that is a complex mixture of both potential outcomes. It is only when the coin falls, when we make a measurement, that it collapses into one definite state, either heads or tails. This is exactly what happens when we measure a qubit. Before measurement, it exists in this rich probabilistic blend. The very act of observing it, of measuring it, forces it to pick a side, to collapse from its superposition into a definite 0 or a 1. This property of superposition is what gives quantum computers their potentially unimaginable power. While 3 classical bits can represent only one of 8 possible combinations, 0 or 0, 0 or 1, 0, 10, etc. At any single moment, 3 qubits in a superposition can represent all 8 of those combinations simultaneously. As you add more qubits, this power grows exponentially. This allows a quantum computer, in principle, to explore a vast number of possible solutions to a problem all at once, a phenomenon known as quantum parallelism. It's not that it's running multiple calculations in separate processors. It's that a single calculation is naturally happening across this expansive landscape of possibilities all at the same time. Now, if superposition was the only trick in the qubit's bag, it would already be astonishing. But there's a second, even weirder phenomenon that truly unlocks the magic: entanglement. Einstein famously referred to this as spooky action at a distance, and the name has stuck because it perfectly captures the bewildering nature of the effect. Entanglement is a profound connection that can form between 2 or more qubits. When qubits become entangled, they lose their individual identities and become parts of a single unified quantum system. The state of one qubit becomes instantly linked to the state of the other, no matter how far apart they are separated. Let's make this concrete. Imagine we create 2 entangled qubits, let's call them Adam and Eve, in a special state where their properties are perfectly correlated. We then send Adam on a rocket to the farthest star in the galaxy, while Eve remains here on Earth. If a scientist on Earth measures Eve and finds her in the 0 state, then at that exact same instant, Adam, light years away, will be found to be in the 1 state. The correlation is instantaneous, seeming to defy the cosmic speed limit of the universe, the speed of light. Now, it's crucial to understand that this doesn't allow for faster-than-light communication. You can't use this to send a message to that distant star. The outcome of the measurement on Earth is random. You don't get to choose whether Eve is a 0 or a 1. You only know that whatever she becomes, Adam becomes the opposite. So, no information is actually transmitted. The correlation was just always there, a fundamental property of the entangled pair. This spooky connection is what allows the individual power of superposed qubits to be woven together into a coherent computational fabric. It's the glue that lets qubits interact in ways that are impossible for classical bits, enabling the complex interference effects that powerful quantum algorithms rely on to amplify the correct answers to a problem and cancel out the wrong ones. So, how do we actually build one of these miraculous qubits? This is where our story of the transistor comes full circle in the most beautiful way. The text points out that the spin of an electron, which can be up or down, is a natural candidate for a quantum bit. And it's absolutely right. Think of an electron as a tiny microscopic magnet, It has a property called spin, and while we can imagine it spinning like a top, it's really just an intrinsic quantum property. For our purposes, we can measure this spin along a particular axis and find it to be in one of two states, spin up or spin down. This is a perfect natural two-level system, a perfect physical embodiment of a qubit, where spin up can represent Suc 0 and spin down can represent Suc 1. Now, how do we trap and control a single electron to use its spin as a qubit? This is where the transistor, our old friend, is reborn. Remember the modern MOSFET, the one with the source, drain, and gate? Engineers are now designing specialized transistors, often called quantum dots, that are gated in such a way that instead of having a channel flooded with thousands of electrons, they can precisely trap and control just one single electron in the channel. This is an incredible feat. It's like taking a bustling highway and engineering it so that only one specific car is allowed on it, and you have perfect control over that car's position and behavior. By applying carefully tuned voltages to the gate electrodes of these transistor-like structures, we can isolate a single electron and then manipulate its spin state using precise microwave pulses or magnetic fields. We can put it into a superposition of spin up and spin down, and we can entangle its spin with the spin of another electron trapped in a neighboring transistor. The profound implication, as the text states, is that the same silicon manufacturing technology that gave us the microprocessor is now being repurposed to build quantum processors. Companies like Intel and startups like Dirac are actively pursuing this path. They are creating qubits that are, at their heart, incredibly sophisticated cousins of the common transistor. This approach holds a monumental advantage, the promise of scalability. Instead of having to invent an entirely new, exotic manufacturing process from scratch, we can potentially leverage the decades of multi-billion-dollar investment and refinement in the global silicon semiconductor industry to etch millions of qubits onto a chip, just as we do with transistors today. It's a vision of quantum computing that speaks the native language of our current technological world. Of course, this path is fraught with immense challenges. Qubits are incredibly delicate. A qubit superposition is a fragile state that can be easily destroyed by the slightest interaction with its environment. A stray photon, a vibration, a bit of heat. This loss of quantum coherence is called decoherence, and to prevent it, quantum processors must be shielded to an extraordinary degree and operated at temperatures chillingly close to absolute zero, colder than the void of deep space. Furthermore, we need to be able to correct for the errors that inevitably occur. Recently, a team in Australia demonstrated a key breakthrough by achieving 99% fidelity in 2-qubit gate operations with their MOS-based qubits. This 99% benchmark is crucial because it's considered the threshold needed to implement quantum error correction, a vital step toward building a large-scale, fault-tolerant quantum computer. And what is the point of this Herculean effort? What are these problems far beyond the reach of any classical computer that these machines promise to solve? The potential is staggering. Imagine being able to simulate the behavior of molecules and chemical reactions with perfect accuracy, something that is prohibitively difficult for even the largest supercomputers. This could revolutionize the discovery of new life-saving drugs and create revolutionary new materials, from room-temperature superconductors to ultra-efficient batteries. In the realm of cryptography, quantum computers could break much of the encryption that secures our modern digital world, but they would also enable new ultra-secure forms of quantum encryption, like quantum key distribution, QKD, that are theoretically unbreakable. They could transform artificial intelligence by rapidly training complex models, optimize global logistics and financial systems to an unprecedented degree, and model the fiendishly complex dynamics of climate change with a new level of precision, helping us chart a better course for our planet. So you see, the journey of the transistor doesn't end in a museum. It is evolving right now in clean rooms and laboratories around the world. From a simple solid-state replacement for a vacuum tube, it has become the engine of a global digital revolution. And now, as we learn to coax a single electron into dancing to the tune of superposition and entanglement, the transistor is being reborn as the foundation for the next great leap in our journey of computation and discovery. It is the bridge from the world we have built to a quantum future we are only just beginning to imagine. From the abstract musings of Heisenberg and Schrödinger to the cat videos on your screen, the journey of the transistor is the story of humanity learning to speak the language of the quantum world. It is a story of taking the most counterintuitive, bizarre, and profound ideas about the nature of reality and forging them into a tool. A tool that amplifies our voices, extends our minds, and connects our world. That simple sandwich of doped silicon, a product of human curiosity and ingenuity, is a bridge between the realm of the infinitesimally small and the scope of human ambition. It is a testament to the fact that when we peer deep into the heart of matter, we don't just find particles and forces, we find the seeds of the future. And so, the next time you hold your phone, or ask a question of a digital assistant, or marvel at an image from a distant world, remember the silent, invisible symphony of quantum leaps and electron waves playing out within. A symphony conducted by a device no bigger than a speck of dust, yet powerful enough to reshape our civilization. The transistor, in its beautiful simplicity, is a whisper from the quantum world, amplified to a roar that echoes across the globe. Good night. Have a deep, calm sleep.